it becomes your asset as well as your students and follower asset as well. So never go for shortcuts and find the easier way. It is not bad that if you find the easier way, but that should not be missing or disinforming people about what you do. Sample preparation is the most tedious of all TM work. And if you remember, I told you one day that when I started microscopy in 1993, and the best microscopist of our department was teaching us electron microscopy. In the first class, he told us that when you have prepared a good sample for TM, your 50% work has been done. You have done 50% of your work. So the sample preparation for TM is very, very important. And if you invest the time, your reward will be the best while doing TM. Otherwise, the bad sample will discourage you. When you are taking good images, good diffraction pattern, it takes you further and further into that area. But if your diffraction pattern is absurd and it's not measurable and calculatable and not analyzable, right? If your image is rough, out of focus, then you don't like it. So what will others say about them? So that is why it is the most important bit of the TM. The quality of your data is directly related to the quality of your specimen. Similarly, the physical dangers, hazardous chemicals, ionizing radiations, and sharp knives. When you are dealing with very fine scale materials and tools and chemicals, and again, the material in itself, whether it is hazardous or not. If it is hazardous and you are finely grinding it, there are a lot of chances that the powder, the particles, the very fine particles, you can inhale them, right? And similarly, your fingers get hurt, injured, and it enters your body, the powder from there, you are grinding it. So you must know the hazardous effects of the sample. And the martyrs of radiation. This is a book written about the Rutherford Appleton Laboratory. I read it, I don't remember exactly, but I read it in 1987 or 88. And many people died because of working with nuclear research and nuclear studies. Because when alpha decay was discovered, beta and gamma decay, and now people are avoiding them. But at that time, people didn't know them. People used to carry the radioactive materials in their pockets, right? So the same thing that if you think with a layman mind, silica, the sand, is the least hazardous material, right? For example, you are on the sea beach, people are playing in sand, right? In other areas where sand is there, and it is considered the least hazardous material. But you look into the silicon, it is silica, SiO2, and if you look into the hazardous effects of silica, it causes many lungs diseases, and many people die from lungs disease, right? Silicosis is the which I remember. There are many others as well. So when you are dealing with sample preparation or experiments, you must know about the hazardous effect of what you are doing yourself and what is happening to the nearby workers. If you are, for example, heating something and the gas emitted from the furnace is hazardous, you run away from the lab. But the people who are working there, you are affecting them as well, right? So the hazardous effects must be known. I had learned a way of making samples that I thought that if I am grinding the sample fixing on the glass slide and then grinding it like that, why not make a space here in my finger? When you press a sample with this finger and the wheel rotates, the grinding wheel, and I was successful in making some very good sample through that. People used to grind the sample up to 100 micrometer through mechanical and manual ways. And I was successful to take it to 1 micron with my finger. But I always hurt my finger with that. So your health must be taken care of in comparison to the sample. So the research doesn't mean that you hurt yourself and you do it. And I didn't know at that time. But if that material was hazardous and it entered my blood, then it has a long-term negative effects on my health, right? So always take care of yourself as well as your co-workers and your students who are working with you. Never risk things. And about the risks of such thing, once I asked a professor that if a machine is running on zero point 0.5 millivolt and the current is about 0.5 milliampere or microampere, can it kill someone? He said no, it cannot kill someone. But if it kills one person in a million, in a billion, why should it be you? If the probability is 1 per million or 1 per billion, why should it be you? So always think about that. That yes, risks are not there, are minimum there. But what does minimum mean? Minimum means there is a risk, although it is minimum. And minimum in terms of 1 per 100, 1 per 1000, 1 per million, and 1 per billion. But why should that 1 per billion should be you? So always take care of these things. You must know what you want to study in your specimen before you begin preparation. Be aware of the limitations of the method you choose. If you don't know, as I told you in the start, that if you don't know about the limitation of argon ion thinner, then you can waste ages and you will not be able to get sample. Similarly, if you are using diamond wheel and you may lose the sample, if you put a small sample on the diamond wheel, it will be in a few seconds, it will be grinded away and there will be nothing left in your hand. So those limitations are equally important. If possible, never touch your specimen with finger when it is thin. Now you are caring about the sample, not yourself. When it becomes thin and you touch it with fingers, then there is number one, there is a chance of contamination. And when you take a contaminated sample to the electron microscope, you are damaging the machine with that because it's vacuum, which is very high vacuum, and it is in such a disrupted in such a way that it can damage the system, the vacuum system, the column of the machine. And secondly, if you hold the sample with a tweezer, then your hand must be skilled enough so that it doesn't break. This is the tweezer. And if I hold a sample and which is 20 nanometer or 30 nanometer thick, and I hold it and I press it, its edge will be broken. So you must be very, very careful even if using the tweezer. And sometimes we had vacuum tweezer, that it was a sucking type tweezer, and we put the tip on the sample side, again on the side, not in the middle of the sample. The middle of the sample is very thin, the side is slightly thick, and we used to suck it with the vacuum tweezer and then put it on the sample holder. And when we completed the study, microscopy was done, then picked up with the same vacuum tweezer and put it in the capsule. It will appear on the camera when you watch the videos, right? This is about 25 micrometer in the middle and about 50 micrometer on the periphery edges, right? This is not finely thin sample. And don't put the sample on the hard place, because when you put tweezer, it will not be able to go down the sample. So when it is placed on a tissue paper, then a slight dimple can help you in picking the sample. This is the thin sample which I made, and it has the thin area. In the middle it is below 20 nanometer, right? These are the samples made following no shortcuts. And when you don't use shortcuts, you have more thin area in the sample. More thin area in the sample means that if this is the 3 millimeter disc, right? You dimple it in the center, so at least this area is thin, right? This middle area is thin, and there is chance of the more area beyond that central area which can be thin. But if you use shortcut and you put a copper ring to support the sample, then you decrease the whole sample up to here, to the middle. Because if this was the 3 millimeter disc, and you didn't use anything else but thin down this disc, so what will happen? This up to here, you can have thin area, right? But if you had a 3 millimeter disc and you put a copper grid, carbon coated copper grid like this, so you decrease the sample area to this middle, and now your thin area will be very small. Because when you are using the argon ion thinning, it will grind the copper grid. More will be spent on the copper grid and very little will reach here. And even if more reach here, still your whole choice is up to here. So that is the damage, the loss due to the shortcut. So always when you do things properly, then after 20 or 30 years, you will feel confident about what you have done and what you will be doing at that time. In the next lecture, I will explain it, but today I found some of my samples and just want to show you that what they look like. In this capsule, you can keep 500 or 600 samples of TM, right? They're so small. And here you may see 1 or 2 samples, but these are more than 20. The sample which are used, this is a copper grid, that how it looks like, right? I put it near the camera so you can see it in the video, but it is this thin area. What is it I'm showing you? One way of the sample preparation is that you totally take the sample. No additional part or piece is added to that. And you grind the sample, you thin down it, then you dimple it in the middle, then you use argon iron beam thinning, and you get the sample. The other way is that this was your sample, you can't exceed the 3 millimeter diameter because the TM sample holder tip has a 3 millimeter space. You are preparing sample for this space, right? If it is slightly less than 3 millimeter, it will fall down. If it is slightly larger than 3 millimeter, it will not settle here. And settling here means you will not be able to correct the eccentric height of the sample. When the eccentric height is not proper, then your information is not reliable. The focusing will not be reliable. So 3 millimeter is must, right? In this case, you took the same sample as the material. You grinded it, you thinned it, and you got the sample, and this is the area. But if you want it quicker, so that you can decrease the thickness below the 100 micron, then the best way is to, this was the sample, and then on the same area, like this. This is a copper ring, and the copper rings are available as 800 micrometer, 1200 micrometer, right? This means that this hole in the middle will be 800 micrometer, right? Or it will be 1200 micrometer, and there are ways. So the less the area is, the stronger the sample will be. And the more the thinner the copper ring is, more area will be there, but the strength will be compromised. And what you do when you fix this, then you grind the other side. And again, you cannot do that with other machine. You will have to use the finger because your sample is very delicate then. And when you thin down, so a little bit sample like this will be left here. And then you take the thin area to the argon iron beam thinner. And in a couple of hours, in 4 hours or 6 hours, you can get electron transparent sample depending upon your skill and quality of your care, that you thin down the sample, but at the same time you don't break the sample. The other way, the third way, is that you get